Hey, hello, and welcome to today's GFG problem of the day. Candy, let's see what the problem has to say. There are n children standing in line. Each child is assigned a rating value given in the integer array ratings. You are giving candies to these children subjected to the following requirements. Each child must have at least one candy. Children with a higher rating than its neighbors get more candies than neighbors. Return the minimum number of candies you need to have to distribute. Okay, so let's see through an example, right? So we'll be giving an array, right, which will have rating values for the children. So there are three children, and each child has the rating value. Okay. Now the requirement here is that each child must have at least one candy, right? Must have at least one candy, and the children and the child with a higher rating than its neighbor should get more candies than neighbors, right? And we have to return the minimum number of candies we have to distribute. Okay. So let's say this is the rating, right? And consider this as the initial resultant array, right? The initial resultant array with at least one candies for each child. Now what they're saying is the child with a higher rating than its neighbor should get more, right? The candies than its neighbor, right? And we have to return the minimum number of candies we have to distribute. So for example, if we consider this case, right, one with rating value one is greater than its neighbor, right? So what we'll do, this should get more candy. So we'll increment plus one, then this one, right? Then this one, what it has? Yeah, it has one candy. So we'll make it one, right? 2, 1, 1 is the current state. If we move now here, 0 is lesser than, this rating is lesser than its neighbor. So we won't touch anything. We'll keep 1 as is. Then 2, right? 2 is greater than 0. So this child has more rating value than his neighbor, right? So what we'll do, we'll increment this plus, we'll do whatever whatever this child has, right? The candies plus 1 will do. So it will be 2, 1. So it will be 2. So now the total number of candies we have to distribute is 5, right? We have to distribute is 5. So this is, as we have to return the minimum number of candies, so we have to increment by 1 only, than the whatever is a neighbor, right? So simple formula can be, for example, let's take another example. The rating with 132, right? The rating with 132, and initial array has 111, this, right? Now this 3 is greater than the neighbor, right? Is greater than the neighbor. So what can be the formula for this? So the formula can be max, right? Max of left neighbor, right neighbor. Whatever is a max plus 1, it should have. So let's say for example, if this one had two candies, right? Right? So what will be the value? What will be the number of candies this child should have with 3 rating? It should have what? Max of L, 1, 2, right? Max of L, that is 2 plus 1. This should have 3 rating, right? This should have 3 candies, basically 3 candies. Okay, because it needs to have greater candies than the neighbor, because the rating value is greater, right? Now let's consider one example, 12, 4, 3, right? Initial, if it is 1, 1, 1 candies, right? So now 12 is greater than 4, right? 12 is greater than 4, right? And so if we consider, now we have to increment the candies for this one, right? Now if we come to 4, 4 is greater than 3. So 4 should have 2 candies. 3, nothing. 3 is lower, so it will have 1 only. Now, ideally 12 should have had more candies. Now, because 4 has 2 candies now, so we'll have to correct this. We'll have to make it 3, right? We'll have to make it 3. So now, if you look at this example, we should have, like, um, maybe already pre-calculated, right? The number of candies the neighbor should have, because see, earlier we had 1, 1, 1, right? So according to the initial array, if we start from here, so we had initially calculated 2 candies, but then 4 was incremented with 2 candies, right? So we had to correct this again. So we need to have some mechanism wherein we already have this handy, right? What is the final number of candies a neighbor will have? Then we can increment the correct value with the correct value, right? Similarly, if we consider this, right, 1, 2, 3, 1, 1, 1. Now ideally, if you consider the initial array, right? If you consider the initial array, so it will be like this one is greater than this one, right? So we'll have 2 here, but 2 is greater than 1. So 2 will have 2 candies, 1 plus 1, right? 2. Now we should correct 3, right? So we should have now mechanism, right? Because we should have mechanism that this already is pre-calculated. We calculate this, the neighbor's value, so that we get the correct value for this one, right? So what we can do, let's consider this example, right? Let's consider this example. What we will do is, we will take 2 arrays, right? We'll take 2 arrays. One will be L to R, L to R, and one will be R to L. So what we'll do for L to R, we'll look at the left neighbors, right? Okay, left neighbors. For example, the initial candies was 1. So what we'll do, we'll start with here, this one, and we'll look at the left neighbor, right? If it is greater than the left neighbor, 4, if it is greater than the left neighbor, then we'll increment whatever the left neighbor has by 1, right? So 4 is not greater than 4 is not greater than 1. Sorry, 4 is not greater than 12. So it will be as is. Okay, it will be as is. This state. And then now we'll come to 3. 3 is not greater than 3 is not greater than 4. So it will be 1 here. Now what we'll do, so L2R is calculated. Left in this, we'll be checking the left neighbors, right? And incrementing the candies accordingly. In this, we'll start from right to left. We'll start from right to left. So what we'll start from here, 4, and we'll look to the right neighbor. Is 4 greater than 3? Yes, it is greater than 3. So it will be whatever candies 3 has plus 1 will do. So we have here for 4, we have here 2 candies now, right? And now we'll come to this 12, right? So 12 is greater than 4. So whatever 4 has will increment by 1. So 3, right? So our L2R, we have calculated L2R and R2L, right? And what we'll do, we will now iterate, right? Through, for example, right, for I equal to 0 to n, right? And what we'll do, we'll have a total. So what we'll do basically is, now we'll iterate through this left to this both arrays, right? And whatever is the maximum for each child, we'll take that. So maximum of 1 and 3 is 3. Maximum of 2 and 1 is 2, right? And maximum 1 and 1 is 1. So we'll have, see, if you see 3 to 1, right? So if you see 12, 4, 3, right? Initially, if the array was 1, 1, 1, right? With each child having a single candy. Now, if you see, right, 4 is greater than 3. So it should have 2 candies, right? 2 candies. 4 is greater than 3, it should have 2 candies. Now 12 is greater than 4. So it should have one more candy than 4. Then the child with 4, right? So it should have 3 to 1. See, we are getting the resultant array 3 to 1, right? So this would be the approach. For example, again, we can take another example. Okay, so this will be the approach. Let's take another example, right? Quick example, 1, 2, 3, right? So what will be the initial array? 1, 1, 1. Now, this is just an example. Now we'll have L2R, right? What we'll start with here, and we'll look to the left neighbor, right? So 2 is greater than 1. So it should be having 2 candies, right? 1 greater than the previous neighbor, right? Now 3 will iterate here, will come here. 3 is greater than 2. So whatever 2 has candies greater than 1 will do. So we'll have 3 candies. Now we go R to L. So we'll start here. We'll look to the right neighbor. So this is not greater, right? So it will be as is 1, 1. So we'll come here. This is not greater than 2. So it will be as is 1, 1. Now what we'll do? We'll take the max out of each L2R and R2L for that child, right? 1, 2, and 3, right? 1, 2, and 3. So yes, if you see 1, 2, 3, right? If you see, now initially it was one array. Now 2 is greater than 1. So it should have more candy, right? It will be 1 here, 2, right? And then 3 is greater than 2. 3 is greater than 2. So whatever the child with rating 2 has, greater than 1, right? So it will be 3. 1, 2, 3. 1, 2, 3 we are getting. So this will be the approach. Let's quickly see the code, right? Let's quickly see the code. So what we are doing, we are taking L2R array. We are initially filling with 1 values, right? Each child should have at least 1 candy, right? With 1, right? And R2L array, we are having another array. We are filling 1. So this may be slightly different in C++. Maybe you'll have to have for loop, right? And then we'll have to initialize with 1 for both the arrays, right? And then simply what we're doing, see, first we are calculating left to right array. So we are starting with 1, right? We are starting with 1, and we are checking the left neighbor here. We are checking the left neighbor, and if it is greater, right? If it is greater, 2 is, for example, right? 1, 2, 3. So if this is greater than this, then we are taking the L2R of 1, right? And plus 1 we are doing, right? We are calculating. And then what we are doing, similarly for R2L we are taking, right? R2L. For example, if this was a case 12, 4, 3, right? We are starting here and we are checking here, right? N minus 2, we are starting from the second last element, right? Second last element. So if you see, and we are checking the plus 1, the next, the right neighbor, right? And if it is greater, then we are calculating this. We are having 1 more candy greater than the right neighbor, right? And then finally what we are doing, we are taking total and max of that particular child, L2R or R2L, right? Max, we are taking max of that and we are adding to the total. So this is a solution. We are adhering to the time complexity and space complexity as well. If you see, right? O of n, O of n. So we have single for loops everywhere. Okay. And extra space we are taking here for L2R and R2L. So this is a solution. Let's submit. Okay, the solution is accepted. Thanks for watching. Please like the video and subscribe to my channel. Thank you so much.